Hello everyone, welcome back. So let's try an example now from chapter 12, going through a vapor compression refrigeration cycle. So this is a long problem statement, but we'll take it one step at a time as we go through this. So we have this basic refrigeration system, and it's attempting to reduce the compression work. So how's it doing that? It's doing that through having a heat exchanger. And so what that's doing is it's going to superheat the vapor that's entering the compressor. So this vapor right here gets hotter, and it's going to subcool the liquid that is exiting from the condenser. And so this liquid right here is going to get colder. And so we're going to use Freon, refrigerant 134A. And let's see here. The evaporator operates at negative 12.73 degrees Celsius, and the condenser at 1,000 kilopascals. What do we want to find? Well, we want to find out what the system's coefficient of performance is when that heat exchanger right here is providing 4.29 degrees of subcooling. And we're going to assume that the evaporator actually gets it to a saturated vapor and the condenser gets it to a saturated liquid. And the compressor magically is perfectly isentropic. So it's idealized. That's okay. We can deal with that. Okay. First off, let's draw this cycle. Now, you don't have to draw these cycles perfectly. That's fine, but having a basic idea of what you're doing is going to be helpful. So first off, it told us that 0.6 was a saturated vapor. It's going down the evaporator. And so that means it's right here on this line, okay? It evaporates because it's low pressure, that's why it's the low pressure line. Then we go through the heat exchanger, which gives it a little bit of superheating, which is why it goes into the superheated region. The compressor increases its pressure and it's isentropic, so it goes straight up. Then we're right here in the condenser. And it told us the condenser gets it all the way to a saturated liquid. So that's why it goes all the way down until it hits this point right here. Then we're back into our heat exchanger again, but this time on the other side, and that's giving us subcooling. So we're now going down to 0.4. And then finally, we go through our throttling valve, which is isenthalpic, but not isentropic, getting us to 0.5, which is some mixture of liquid and vapor, and then that finally all vaporizes as I go through the evaporator. So that's how you would draw this cycle. Now, what we're going to be trying to figure out is, how much work does it take to run this? What's my heat leaving? What's my heat entering from the evaporator? What's my heat exiting through the condenser? All those things are kind of important for us. And if I have all those things, I can go ahead and find my coefficient of performance. So we'll just take it one step at a time. So first off, it said that the refrigerant leaves the condenser as a saturated liquid. Okay, saturated liquid, that is 0.3 right here. It also gave us the pressure. It says the pressure was 1,200 kilopascals. I do realize I had a typo earlier on. I was saying that was 1,000 kilopascals. So I'll have to go back and fix that. But for now, we'll keep on going with this one. So 1,200 kilopascals. And so it's a saturated liquid. That means that my enthalpy is just the enthalpy of a saturated liquid. And it's going to be 117.79 kilojoules per kilogram. Okay. So it says the refrigerant gets 4.29 degrees of subcooling. So that means that whatever my saturation temperature is at 1,200 kilopascals, well, I'm going to be 4.29 degrees of subcooling below that. So if we actually go to our tables, and I'll jump over there so I can show it to you. And here we are. I can go down to 1,200 kilopascals, and I can find right here that my saturation temperature is 46.29 degrees. Since it's 46.29 degrees, I go down by 4.29 degrees, and what do I have? A nice round number. Thank you, problem maker, for doing that. Okay, let's jump back to the PowerPoint. And so we have a temperature 4 of 42 degrees Celsius. Now, yes, this is subcooled, but as I said before, when you're subcooled, you just say, I'm more or less a saturated liquid at this particular temperature. And so I can check my tables. I find 42 degrees Celsius, and I can say that, okay, the enthalpy of a saturated liquid at 42 degrees Celsius for Freon, for that refrigerant, is 111.28 kilojoules per kilogram. Okay, so that's point 3 and 4 done, working our way through it. Now let's go to point 5. And so it's really easy. It just says throttling is isenthalpic. So my enthalpy at point 5 is just my enthalpy at point 4. Nothing too bad there. Okay, point 6 here, it says it leaves it as a saturated vapor. So we know what the temperature is. It's negative 12.73 degrees Celsius. And so if I go to my tables, I find a temperature of negative 12.73 degrees Celsius. As a note, if you're looking at the temperature tables, you're probably not going to find that. So if you don't find that nice number in the temperature tables, check the pressure tables too. So let's do that right now and see if we can find it. Jumping over the tables now. So here I am in my saturated refrigerant temperature tables. If you look right here, you're not going to find negative 12. Negative 12, negative 14, I would have to interpolate. Don't interpolate. Before you start interpolating, check both tables. Because if you can find the temperature in either one of these tables, you're golden. And guess what? Right here, for 180 kilopascals, its saturation temperature is negative 12.73 degrees Celsius. I don't have to interpolate. I just use the saturated vapor properties for this row. And so I can go all the way over here and find the enthalpy of a saturated vapor to be 242.9 kilojoules per kilogram. So don't forget that. It's a really helpful detail. Now let's jump back. Okay, here we are. So, another thing we realize, because we found it, is that the saturation pressure for this particular temperature is 180 kilopascals. So we actually know what our little line is down there. And that means we now know the pressure for point 1, because it has to be the same pressure. Okay, but what is the enthalpy of point 1? Well, let's deal with it, use a heat exchanger to help us out here. So I know the amount of heat that is being taken away from my saturated liquid over here is equal to the amount of heat that is being added to my saturated vapor right here. So that energy is going from one to the other. They have to be the same. And the great thing is, I already know this difference. I know that difference in enthalpy. I also know that my mass flow rates have to be the same, because it's only one fluid stream. And so that means since I know this, this, and this, I can solve for that last remaining enthalpy, H1. And it comes out to be 249.91 kilojoules per kilogram. Okay, we only have one more point and then we are finished with all the points in enthalpy. We can calculate the coefficient of performance. And so let's go ahead and do that. So we're going to need to figure out what our entropy is in order to figure out where we are at point 2, because we're going to need to know the entropy at that point, or at point 1 to find point 2. So we interpolate and we get this entropy. How? Well, I knew what the pressure was, 180 kilopascals. I knew my enthalpy, so I could actually find my entropy. And so I'll go ahead and show it to you right now. Why not? We'll keep on jumping back to the tables. So let's go to the superheated tables for 180 kilopascals and find this enthalpy. Okay, we can do that. Won't be too bad. Here we go. So here I am, and I have a pressure of 180 kilopascals. Thank goodness. I know the enthalpy, and so I would look in here to find my entropy. And I've forgotten what the enthalpy is off the top of my head. Okay, it's 250. That is in between these two values right here. And so my entropy was somewhere between these two values right here. So I'm going to have to interpolate to find my entropy. I've done that before, so I'm not going to do it right now. I just wanted to show you how I find the values I would need to interpolate. Okay, so finally, we're going to have to interpolate using the compressor. So we jump up to our old pressure. We're still superheated here. And we know that our entropy is the same at point 2 as at point 1. And so for a pressure of 1200 kilopascals, I would do the exact same thing I did last time, just now I'm finding the enthalpy. I'll get my enthalpy as 290.6. So I interpolated here using the enthalpy to get my entropy. I interpolated here using my entropy to get the enthalpy. Did one and then the other. So with this, I have all of my enthalpies. I have every single point here, all the enthalpies, and so I can now calculate my coefficient performance. So for a refrigerator, I care about how much cooling I'm doing. Not how much I'm heating up my house, but how much I'm actually cooling the food, the medicine, whatever it is. And so it's this value over my work in. And so with that, I can solve. So the amount of heat being added into my fluid from my food, whatever is being cooled, is simply equal to the difference in enthalpy between 0.6 and 0.5, right here. And the amount of work that it takes to do all this, to run this cycle, is simply the work of the compressor, which is the difference in enthalpy between 0.2 and 0.1. And so I get a coefficient of performance of 3.195. Is this good? Is this bad? We would have to compare it to a Carnot refrigeration system to see how good it was doing with second law efficiency. But all in all, that's it for this problem. Thank you all so much for paying attention. Hopefully this helps you, and I'll see you all next time. Bye-bye.